Welcome back to EPE 2025. My name is Ed Kiebler. Sitting next to me is the absolute ring guru when it comes to piston rings and anything related. This is Keith Jones from Total Seal Manufacturing. Keith, take it over.
Thanks, folks. Appreciate everybody being out there. Appreciate everybody being here. We've had some great presenters before us. These are the guys that when we were going to school, they were in the front row. They were asking all the questions. They were writing all the notes. We're the guys that were sitting in the back of the class going, wow, that's kind of cool. So what we're going to talk a little bit about today is a little bit about rings, a little bit about oil, a little bit about honing, a little bit about pistons. We're not, we've only got about an hour's worth of time, so we can't really deep dive any one subject, but we'll kind of hit a few different things here. So one of the questions we get asked every year, how many guys out here and in the audience out there, how many people have gone to the PRI show? Everybody. Okay, what's the one question we get asked every year at PRI? What's new? Let me tell you, it's hard to reinvent the wheel every year. So we're constantly developing new materials, new products, new coatings, new profiles, but one of the things that's new is a whole lot of new equipment. I've got to tell you, Matt Hartford, my boss and friend, CEO of Total Seal, and the group, we are owned by a company called the Promise Group, but these guys are really good, really active, very involved with the company, unlike a lot of other groups out there. These guys are pouring money into our place like it's literally growing on trees. I bet you I'm just speculating, $3.5, $4 million worth of absolutely state-of-the-art equipment within the last 2 years and more coming. We are just trying to elevate our game and increase our productivity every single day of the week because all of that comes down to manufacturing a better part and trying to do it faster and less expensive. How many people hear that today? We're trying to do it and bring the price down. So being able to improve our capacity every day, we used to do about 1,500 rings a day. We now do 15,000 rings a day and looking to add more capacity all the time. So with that said, that's one of the new things that's new at Total Seal is I call that Big Blue. That's an entire ring line from nothing to something, and it only takes 2 people to run it. 3 if you really want to do it nice, but you can get away with 2. But to go into, to piston rings, what is the job of a piston ring? What does it have to do in this world? Well, it's got a lot of jobs to do. It's got to seal the combustion event. It's got to keep all that explosion above the top of the ring. And why is that? Because we're driving the piston. We have to capture that force, and we want to move that force in a downward motion. Why? Because we want to send that to the connecting rod, which we're going to send that to the crankshaft. We're going to take that from a vertical motion into a rotary motion, send it to the differential, and hopefully set a new world record with your engine because the rings are sealed up so damn well. The other problems that it has to deal with is it's got to move heat. About 80% of the heat that goes through your engine goes out through the rings, into the piston, into the wall to the water, water into the atmosphere. We've got to get rid of that heat. More power we produce, the more heat we're going to generate. Cold fusion is still a concept, though I think it's a reality. They're just not telling us. But also, we've got to maintain proper oil control. We've got to keep that oil out of the combustion chamber. We want to keep that engine in happy as dry as we can. Current thinking, and I've been doing this a long time. Just to back up a little bit, I've been in this business for about 40 years. I've been with Total Seal 28 years. And there was a point in time where people thought, hey, if it's not smoking, it's not fast. It's got to be huffing and puffing around the pits. Crack that throttle, big blue cloud comes out because I've got all the friction out. Well, what we found, and we'll say Mr. Morgan would certainly back that up, a clean combustion chamber, a dry combustion chamber is a happy combustion chamber. We don't want oil migration. So we're actually seeing oil tension starting to slide back up a little bit, away from that slightly hazy, super low friction, super low drag to that nice, clean, dry combustion chamber. So it's the ring's job to help control that oil. It's one of the things that's many parts of the puzzle right here in keeping good oil control. And we've got to scrape that oil back down into the sump. So going back to, we'll say, I believe it was Lake would know the number off the top of his head. Yep. 1857, I believe it was John Ramsbottom invented the piston ring for the steam engine. We started off working with materials, just plain old cast iron. So we're working with just good old gray iron, same stuff you cook on a pan with, and we'd make a piston ring out of that. The problem with those materials is they're very brittle. They're very porous. They've got a lot of porosity, and they're not very strong, and they break very easily. So we moved into ductile iron. So a lot of us have used a ductile moly ring. How many have used a chromoly ring? Well, sorry you didn't. We don't make rings
trick
out of
question.
tubing. It's a trick question. That's talking to the coatings that are on the ring. It's either chrome or moly, and it's a common misconception. We make chassis out of that material, out of chrome moly, not piston rings. So we're talking about the coating. You hear the word ductile moly. Ductile's the material it's made out of. Moly's the coating that's on top of it. So that's the material. That's the coating. What does iron offer? Great thermal transfer. Moves heat extremely well. But as far as coatings, you coat it with chrome or we coat it with moly. It's really about all the coatings that it really, really likes. Big problem today that we've got from a manufacturing point of view with iron-type products is one, is a lot of guys in this industry, from Rottler right here, manufacturing these wonderful pieces of equipment to cylinder head materials, all of these stuff. All of this material's got to be poured. It's got to be done in a foundry. And what don't we have very many of in this country anymore? Foundries. It's hard to come by irons. It's hard to come by aluminums. And we're doing everything we can to bring them back into this country, but a lot of that work has gone offshore. So one of the problems with doing an iron-based piston ring is you got to pour a lot of it. It doesn't come out of a log or a piece of pipe or a piece of tubing. It can, and that's how you did it 150 years ago, but it's not how it's done today. So if we're working with iron-type rings, we've got to build a lot of them because we have to pour that material. So what we've done is gone into steel manufacturing. Rings in the world today are all going steel. Steel top rings, steel second rings. Why? Because it comes out of a coiled or drawn wire. I had more illustrations of it. I'll apologize. I've had to kind of trim this down a little bit. Try to keep it within an hour, but trust me, that's not going to happen.
No.
We have a tendency to go a little long. But steel rings come out of a drawn piece of wire, and we can take that wire and we can coil it, turn it into a circle, produce a part. One of the things about a steel-based ring or rings in general, misconception, rings aren't round. Rings are actually cam-shaped. So we do a process called cam coiling. We put that ovality into the shape of the ring so that when it's open and in the manufacturing state, it's a workable part. But when we close it down and compress it and put it in that cylinder, now we've got a round part. We refer to that as light tight. So one of the things that I don't have a slide on but we can talk about is an easy test or an easy check when you're putting an engine together is simply take the ring. You can put a ring in a cylinder and literally take a flashlight. Bring it up around the bottom of the ring, bring it around the cylinder, and look for any kind of light between that ring and that bore. Now, that can be a little difficult because of ambient light, other things that are going on. So if that's a problem, hang that ring on the piston. Simply put that compression ring or that second ring on the piston, put it in the cylinder, push it down, make sure it's squared up, put that big bright light on the bottom of the bore. The piston itself is going to block out all the light coming up through the center. You'll only see that light around the peripheral. You're going to see, if you see any significant areas around that ring not touching the bore, you need to kind of stop, take a look. Either I've got a bore that's not round, or I've got a ring that's not round, something that's gotten bent, something that's gotten damaged. Now, it's not uncommon to see, especially with Mark sitting right here knowing about surfaces, you'll get what is in my industry referred to as bury light, little pin dots, little spots around that where there's that little high spot. There's that, Mark was looking for the word earlier about the dirt. I just call that a tick turd. So you've got that little thing on the bore. It's lifting that ring up slightly, and you're going to see that light. So if you see that, simply cycle that ring up and down the bore on the piston a couple times and see if that goes away. 99% of the time, it's just a small amount of little debris that's sitting on top of the cylinder, and that cycling of the ring up and down will get rid of that very quickly, and you'll now have that light, tight part. But that's a great way to check a ring before you finish the assembly. Make sure everything's right. Bores are right, rings are right. Parts that you just spent all that money on are light tight because it makes all the difference in ring seal and how quickly the engine comes together. Now, moving into this world of steel that we're talking about here, there's all kinds of steel. There's stainless steels, there's carbon steels, 9254s. There's a whole family of different steels, all the way into M2 into tool steels. Today, we're very honestly, we're moving into ultra exotics like Inconels and cobalts and stellites. We're constantly pushing that envelope because we're being pushed. Nobody ever comes at us and asks us for less. Okay, again, hands up. How many people have come into your shop and asked for less power? Come on, hey, man, I know you build a good piece. Can you knock about 40 horsepower to my junk for me? No. Whether they can use it or not, whether they need it or not, they always want more. And that's racing. That's performance. And that's what we're always being asked. produce a ring that will handle more temperature, more heat, with less drag, less friction, and that pushes us into all kinds of exotic materials today, and we're now working with those. So the question that also arises from that was, which one's right for my engine? What do I need? Do I need tool steel for my Volkswagen? Probably not unless your Volkswagen's got 1800 degree EGTs, but if you want it, you can have it. But a real easy way to tell is what I call, the forensic analysis, it's probably not the right term to use, of disassembling an engine. You go to a really good engine shop and you'll never see these guys throwing one together in a day. It's going to take a week. They're looking at everything going together. They're checking, they're double checking. They're looking at every piece of geometry in this, surface finishes. They're looking at everything. You need to spend as much time as that taking it back apart, because all the parts are telling you a tale. I can tell a million stories, as Ed knows. I had a engine builder that I was working with, sprint car shop. I just happened to go into their shop that day, and they're like, we keep having this accelerated bore wear problem, and we just don't get it. And I go in there, and the cylinders are just wiped out. These things have got about 410 sprint cars, got about 10 nights on them. They're used, but they're not used up. So I'm looking at it. We look at bore finishes of what they were down in the bottom of the cylinder where it began life versus what it is now, and the amount of wear that I see in that cylinder. Unless these guys have got the fuel curve completely out in left field, there's no way we should be seeing this much bore wear. There's something else going on. I said, do you happen to have the drain oil coming out of this thing? Well, yep, I sure do. I said, we need to get that out of there. We need to get that off to our good friend Lake Speed. Let's get that oil analyzed. Let's get it looked at. And what did we find? We found titanium. It's got a whole bunch of titanium in that oil. Well, that's very abrasive. We found our wear problem, but why? Well, why was because they weren't really paying attention to everything when they were knocking it apart. What was going on? Keepers in the titanium retainers. Come to find out, they weren't coated. They did not have that nice PVD coating on them to prevent the interaction of the wear between the two parts, and we were literally contaminating all that oil with titanium. We did not have an engine failure at that time, hadn't happened yet. But because no one was really looking that closely at all the parts when they were taking it apart, they didn't see it, and this happened engine after engine. Well, once we had that oil analysis back, we found there's a whole bunch of titanium. Where is it coming from? Well, it's certainly not coming from the rings, and it got them looking. So my point being is, it's real important to really look at all the parts when we're coming back apart, because it's going to tell you a tale. In the ring world, the question's always asked, what ring do I need? What material do I need? Well, the easy thing is this little slide that's up there right now, the free gap on the ring. We build our engine, we've got that build book, we're checking all our clearances, we're writing it all down. What's my crank end play? What's my rod side clearance? We're looking at everything, writing it all down. Well, one of the numbers you need to be recording is the open gap or the free gap on the ring. What is the gap on that ring just laying on the table? Write that down. That speaks to temperature, and temperature is what dictates what material the ring is going to go into the engine. If I start looking at iron-based rings, I'm looking at rings that are going to anneal somewhere between 11 and 1200 degrees. I start moving into the worlds of stainless. I'm looking into the middle, 1400s, into those worlds. Into the tool worlds, I'm getting up into the 1900 degree range. So that ring will tell me a tale. If that ring's been overheated, it's going to lose its open gap. It's going to lose its free gap when it comes apart. So we're going to close that gap up. The other thing we may have is the end gaps of that ring may no longer line up to each other. They may droop or starting to creep the metal. Some people refer to it as annealing. It's referred to as creep. We're creeping the material. That's a great way to tell if you've got the right ring material in your engine. Now, the other thing it'll tell you as well, maybe your tune-up's way off. Maybe you've got the right ring, but you're simply got your tune-up that far off. The other telltale that goes with that is looking at the rest of the parts. How do the plugs look? How do the bearings look? One of the things I will say to people all the time, people look at bearings to look at, for detonation problems in an engine. The fuel guys tune their engines off that top rod bearing. Where you'll see it in a mild detonation situation way before you'll see it in the bearing is look at the top side of your wrist pin bores in the piston. You start seeing darkened up wrist pin bores. You start seeing a little galling in the top side of that wrist pin bore. You will see that problem in the pin bore in the piston way before you'll see it in the top of the bearing. So those things, if I've got a ring that's losing its tension, but yet I'm seeing aluminum on the plugs, I'm knocking head gaskets out, I'm killing bearings, I know I've got a problem there. But if everything looks great, everything's coming apart great, but I'm seeing this happening to the rings, that simply tells me I got to up my game. that material that I'm using on that ring is simply not tough enough for the environment that I'm exposing it to. So that's a great way to tell if what you have in the ring is correct. And I'm going to try to make this quick because I got to let my good friend Ed here have a little mic time. So one of the things that's also changed is coatings, the face coatings on the rings. We've got some pictures here going from the top left all the way around is just plain old cast iron, no coatings. This is what we ran 100 years ago. The rings are easy to machine, simple to make, but they kind of wear out fairly quick. Molybdenum, moly, on the periodic table. It's out there, but it's becoming harder and harder to get. It's becoming more and more expensive. The upside of moly, and this will kind of come into the cylinder portion of this, and as Mark's done some tremendous advancements in bringing surface information to the real world, and we can show these in a little bit. And we sent some rings to Mark so he could put them in and 3D analyze them, and you could actually see what the ring cylinder surface is like, but what's the actual face of the ring look like? And Mark and I were talking a little earlier, and he was pretty blown away at what the moly on a ring looks like. Moly's about 40% porosity. It holds oil like a sponge. It is, I'll call it I hate to use the word bad, but maybe the uninitiated engine builder's best friend. It's going to let you get away with all kinds of surface finishes, all kinds of things. Heck, you could put a 2x4 and a piece of 220 grit in there, swish it around in the board, and a moly ring would probably work okay on it because it's holding all the oil. It's not demanding that the cylinder surface retain and hold that oil to keep everything lubricated and happy. But moly's going away. Moly's becoming more difficult to get. It's becoming more expensive. And the really big problem is in today's world with real little thin rings, narrow parts, detonations that run, engines that run and knock all the time, moly comes off. It flakes, it chips, it does not stick well. So if we're in a performance application where we've got big compression, nitrous, blowers, turbos, things like that, though molybdenum is a friendly product, it is not a race engine's best friend. And then we've got the old school chrome. That's electrofusion chrome like you put on the bumper of a 57 Cadillac. It's the same thing. Lumpy, bumpy, nasty stuff, takes forever to wear in, but it wears extremely well. Then we enter the world of PVD style coatings. So physical vapor deposition coating, we use a lot of PVDs. The first one is tungsten carbide carbon. This is similar to molybdenum. It's not as porous, but it's about the same hardness as moly. It seats up very quickly, wears well. Chrome nitride, titanium nitride, diamond-like carbon. We're familiar with all these coatings. They just are harder and harder. We keep moving up the scale in wear durability. DLC is one of those coatings. We always say we can't run alike coatings against themselves. Well, DLC is one of the ones that will. We've actually run DLC-coated rings on DLC-coated bores. Performs extremely well. Very hard surface. Wears extremely well. The titanium, just like coating the drill bit. We're putting it on there. Does it cut better? No, but it lasts longer. Same thing on the piston ring. The softer coatings do seat up faster, but the harder coatings last longer. So we have to find that right balance, that right compromise of how quickly does it need to seat up versus how long it has to last. But one of the latest innovations that we've got, we just came out with this year, working with some coating companies, one of the things with most of these coatings is they don't like to what I'll call stack up. They don't like to be over-coated or double-coated. They don't stick to themselves very well. But we worked with a company that's developed a multi-layer process, and we're actually taking tungsten carbide carbon and putting it over top of chrome nitride. So we have a coating that seats up like a moly, but wears like a chrome. So if you're in a dirty environment, maybe over-fueled, got a lot of junk going through it, and you're prone to wearing rings out, well, we've got a coating that seats up right now, so you've got the numbers on the dyno. Your customer wants to see, whoo, look at that. Got a whole 15 seconds of loaded runtime on it, and look at those numbers. But we've got the chrome nitride that's going to last and give us the longevity that we want out of that product. So that's one of the newest things we've got going on is this multi-layer coating or dual-layer coatings. We always talk about rings, ring tensions, and one of the things to understand is pressure is force over area. So force, how hard is that part pushing against the cylinder wall versus what we'll refer to as drag. These are two different things. So I wanted to kind of just throw that out, because the reason I say this, I get a lot of guys that will take a ring set and they'll pull it through the cylinder with their $12 fish scale, and go, man, it took 18 pounds to pull that through. Well, you're measuring, in this case, you're measuring friction. You're measuring the force it's taking to move that up and down the bore. What does it take to move? Cylinder finish directly affects how you scale that part. This is not an accurate measurement. It is what you have in the field as a tool to use, and it can be used, but please understand, this is not an accurate way. This is not how we measure rings. I had a customer just this morning texting me, fish scaling his parts, pulling them through, telling me his oil rings make 8 pounds of tension. And I'm like, no, they're actually 15 pounds. I tested them myself. The difference is you're running them against a Nicosil coated bore, which is very, very smooth, versus a honed iron bore, which is significantly rougher. They're going, even though it's exactly the same part and it's got exactly the same pressure, the drag or the friction is completely different. So scaling the parts is a very inaccurate, skewed way of telling what the part's actually producing. But here's a little graph just kind of talking about ring tensions, going back to the days, the old 5/64 rings. You can kind of see the scale. The old 5/64 rings that were in, mom and dad's Cadillac or in, Uncle Bob's pickup truck. The old 5/64 rings are about 7.5 pounds per ring of force. As you can see, going down, and we stop on this particular, scale at about 0.7 millimeter. We all go all the way down to 0.5 millimeter today. That's 20 thousandths thick. So to give you a visual, an oil ring rail on your 3/16 oil ring, that's 24 thousandths thick. We're producing compression rings that are thinner than your oil ring. The force on these are about a half a pound, about 0.5 pound of force. But what we work with, talking on that other scale, is what we'll get into as Ed gets into the honing a little more, what we call unit pressure. What's the actual pounds per square inch that it's putting on the bore? And we can adjust that through the thickness, through the material, and the force that it generates. And I can have this nice little thin part, but yet have enough actual unit pressure or force against the cylinder wall to get that proper ring seal and to get that oil control. But the one I wanted to really kind of touch on is oil rings. And these things kind of get a bad rap. So, I'm going to throw the question out again. We always hear the word standard tension and low tension. What does that mean? What is standard tension? Well, there's a specification on a 3/16 oil ring, standard tension on a 3/16 oil ring, and in this particular bore size, which is about 4/185, they're about 20 pounds, plus or minus 2 pounds. That's standard tension. A low tension 3/16 oil ring at that same bore size is about 16 pounds, plus or minus 2 pounds. But a 3 millimeter oil ring, standard tension, we're back to that word standard tension, it's only 10 pounds, plus or minus 2 pounds. So this is something to be aware of when we're speccing ring packs and looking at the applications of what they're being used in. So we take Uncle Bob's Chevy truck that I just talked about. We put a 383 stroker kit in it. We put a high volume oil pump, so we're moving 25% more oil into the cylinder. And then we buy a modern ring set with a 1.5, 3 millimeter oil ring in it. We've cut the oil ring tension in half. We've increased the oil volume 25%. We still have the stock oil pan on it, and we wonder why it burns oil. So we always have to be aware of what does standard mean? What does that number truly mean? And is it right for the application that we're working on? So we'll just say, ponder that thought. But the efficiency opportunity is there. This is just a test that was run using some of the, and I apologize because I can't see that. What size are we working on there, Ed? I think 16/16 versus some 0.7s. That was actually just with the simple ring change on that was about a 25% or 25 horsepower gain. There was also a significant reduction in wear metals. It cut the wear metals in the engine by half. So absolutely, big difference in getting that ring thickness down, that drag down. It does directly correlate to more power, less temperature, less heat in the engine, less friction, and reduced wear metals. But one of the things that we're always trying to do at Total Seal is we'll say eliminate leak paths. So we talk about blow-by in the engine. Blow-by is coming from 3 places: end gap of the ring to the ring groove itself. So you got to remember, that clearance between the ring and the ring land, that is a place for blow-by to get through. It's also a place for oil to get through. And then, of course, the also important interface of the ring to the cylinder itself. We'll say that's where I kick it off to my friend Ed, because we'll say that's their job.
Yep.
So Total Seal piston rings has been around since 1967. Our gapless piston ring, which is what we're known for, was actually came out of a rotary engine design. The founder of the company, Joe Moriarty, created a rotary engine, not a Wankel. We actually still have it. It's sitting upstairs. One of these days, we're going to put it back together and put it on display. It's a very, very innovative design, but our gapless piston ring came from the design of that engine, and it's a very simple way to block off that end gap. Now, talking with Darren yesterday, we're talking about ring seal, and with all the advancements, all the work that they've done on camshaft, cam core size, cylinder head, manifold, all of that work that they've done is for naught if the ring seal on the intake stroke isn't as good as it can be. The better we can make that, the better it's going to draw that air and that fuel into the engine. Now, we get into forced induction. Well, we've got a hairdryer, supercharger sitting on top, shoving it in there. But in the world of the normally aspirated engine, all of that work, all of that money, all of that time, all of that R&D is out the window unless that ring seal is as good as we can get it. So always remember, all that work that you do, and it's just not quite the number you're looking at, we've got to look at what's it doing on the intake stroke. And that's all about trying to improve that ring seal. So we fixed the end gap. We got that fixed with the gapless ring. But the next thing is trying to fix the surface of the ring. So you go out, you spend your $3,000 on the best pistons you can buy. They cut the best ring groove. It's flat, it's parallel, it's great to 20 millionths of an inch. It's, wow, is it a good ring groove? And then we put a $100 set of rings into that incredibly good piston that has surface finishes on the ring that look like something out of the Pacific Ocean. There's high spots, there's low spots. These are your sealing surfaces. So again, one of the things that we've done is gone away from typical ground piston rings. Most rings are run through a Blanchard grinder. If anybody's seen one, it's a big dual disc grinding machine. It blows rings through it like a bullet through an AK-47. It is pop, 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 pop. It is just cranking it through those machines. And as you look at that upper left picture, you get this rough, kind of nasty looking ring that's got lots of high spots and low spots. When you look at most piston rings that come off the shelf, they're coated. They've got that coating that's on the top and the bottom of the ring can be a manganese phosphate. It can be oxide. It's what I like to call Bondo for piston rings because it covers up a lot of atrocities. If you take that off, if you get that coating off of that, you can do it through, a little muriatic, some things will take that coating off without affecting the actual surface. You will see what the ring actually looks like underneath that coating. That coating is there to stop the ring from rusting when it's sitting on a shelf in Alabama. On our shelf in Phoenix, I could put it in a swimming pool, it ain't gonna rust. It ain't happening. It is a dry heat. But you send it somewhere where we've got humidity, it rusts. And that's what that coating is there for, is to prevent rust. It also covers up the surface. If you look at these other surfaces, we lap our rings. We have a patented ring lapping process. We're able to hold much, much tighter tolerances. Typical production ring, you've got a plus or minus thickness of 5/10 thousandths. So meaning, let's say it's an 043 ring, you've got a thousandths window that ring falls into a production spec. Well, you're trying to hold 4/10, 5/10 clearance ring to ring groove. How are you going to put in a ring in a groove that's got a thousandths variance in thickness? All of our AP, all of our steel rings, we hold to within a 1/10 and a half. Our diamond finish rings, we hold to 50 millionths of an inch. This is the lapping process, and you can see the differences in the surfaces shown on the screen right now. And I apologize for that because you're looking at one picture, I'm looking at two pictures.
Yep.
You're not seeing what I'm seeing, but if you look at the upper left, that's the Blanchard ground ring. The next picture is our AP coming off the early stages of our lapping process. And the final is our diamond finished ring. And that's where we're holding RA numbers below 2. Tolerances, like I said, plus minus 50 millionths of an inch. So we're holding a very flat, very tight tolerance ring that allows the racing world to fit those extremely tight tolerances to eliminate ring flutter, to eliminate blow by, to get that improved ring seal on the intake stroke. But then the next surface we're working on is that critical ring to cylinder interface. This is the one where we're doing everything we can to control the profile of the ring, get that barrel shape or that taper, that Napier, that really do the best job we know how to do. We've coated it, we've made it great in the ring groove, but next I've got to seal that ring to the cylinder wall. And what is that seal? How do I do that? It's oil. And oil, again, I keep referencing to our good friend Lake. Lake used the term oil is the gasket. Oil is what seals that ring to the cylinder. So we're holding oil on the bore. We want that ring to seal, but one of the things we want to talk about, we're going to talk a little about, got a couple more things we're going to do, and then I'm going to turn it over to my friend Ed. One thing to remember, what do we have going on with that piston? It's moving up and down. It's constantly moving. Well, what's constantly happening during that stroke? Earlier, Darren was talking about mean piston speeds. That speed's not linear. It changes. It's always changing. So where's the piston speed at exact TDC and exact BDC? 0. It's not moving. It stops. Changes direction, goes the other way. So as the piston's moving down the bore and approaching mid-stroke, the piston speed is going up. Piston's accelerating. Hits mid-stroke, what's it doing now? It's decelerating. It's slowing down. It's getting ready to hit bottom dead center, change directions, go the other way. So it's constantly changing speeds. It's not linear. Well, why does that matter? Because there's 4 different levels of lubrication in a cylinder. We've got the very top slide, no oil. There's no oil between the parts in the cylinder wall. Metal to metal contact, full boundary. We've got full contact. That's your engine shut off. Start the engine up. We've got motion. We're starting to move some oil around. What do we have? We're moving into the bottom slide. We're moving to heavily loaded condition. We've got a fair amount of contact. Engine's warming up. That's why we want to let it warm up, start to build some oil film up. But we're also starting to accelerate. We're bringing the RPM up. Things are happening a little faster. We start moving from moderately loaded to lightly loaded conditions. So at top and bottom dead center, we're running in a moderately loaded. There is some metal-to-metal contact. This is why we see accelerated bore wear in the top, and we see more bare wear at the bottom. And especially at top where we've got fuel. We've got fire, we've got combustion, we've got pressure, we've got heat. We see most of the wear up there because we're running in a moderately loaded condition. We're in the middle of the bore, we're running in what we refer to as a lightly loaded condition. So I'll pop the next slide up, and for everybody out there, this is your moment to go, aww. That's your ring on your cylinder wall. I want that ring up on top of the oil. This is what we're trying to achieve. So imagine water skiing. You're sitting in the water. You're waiting for like one of my friends trying to rip my arm out of my sockets. Gonna stab that thing. We want to get that up on top of the oil film as quickly as possible so we can keep that part lubricated, increase that ring seal, and move heat. Got to move thermal transfer. So we want the ring riding on top of the oil, not below the oil, not on the cylinder wall. That's where all your wear happens. So trying to keep things moving along, I want to talk a little bit about pistons. So we've talked a little bit about rings, modern pistons. If we look at the upper left corner, again, back talking about John Ramsbottom in the steam engine, that's what we had. We had straight up and down bores. We got straight up and down pistons. Can run very tight piston to wall clearance because we're cast. We have very, very little rock. So one of the banes of our existence in the ring world is piston rock, excessive amounts of rock over coming through top and bottom dead center. People always fight this in a piston. We're talking more temperature, the way pistons grow and expand. The modern piston, if you look at the upper right, is more the shape of what we see today. We've got a barrel, what I like to refer to as the keg of beer versus a can of beer. So you look at that keg shape, what's that allow? Well, it allows the piston to rotate on the pin, but we've got taper going up and down. We're expecting the piston to expand because of temperature at the top and at the bottom of the skirt, and to help guide the piston and stabilize it coming through top and bottom dead center. We want a very, very stable condition. But the piston guys have got a really difficult job. So think about it. Iron block, aluminum block, water-cooled, air-cooled, gasoline, nitro, alcohol. All of these things affect temperature. So how can one piston shape be right for everything? They start off with their shape that they've got. They supply you a piston, and most of the time it does a very good job, but not every time. Sometimes we've got to take that piston back out, send it back, let them look at it, look at places where it's hit, where it's not hit. I like to take a fresh engine, a new piston that I've got a project I've never worked on. I paint that whole piston with red machinist Dykem. Because when I pull that engine back apart, it is going to show me everything that's touched or not touched. Places that I expect contact to be and places that I don't expect contact to be. If I see a lot of heavy hitting down at the bottom of the skirt, I don't expect that to be there. I'm going to get with my piston guy and say, hey, what's going on here? We need to fine tune this. I'm not going to blame him. I'm not going to say they did anything wrong. I haven't given him enough data yet to make sure the shape of my piston is correct for my application. So I'll send it back, let him work on that. And he can go, oh, well, I can pull that in another 10 thousandths, and I need to bring that out another 4 thousandths and fine tune that piston for that application. But knowing those places where it's hitting or not hitting is very, very important. The next problem is the bottom row is the infamous stroker. So just because a crank does fit in a block doesn't mean it fits in an engine. There's two different things. And this is something we battle continuously. So let's take an LS platform. How much stroke fits into an LS engine and keeps the piston in the cylinder? 3,900. How many people have put a 4-inch crank in an LS? How many people have put a 4,100 crank in an LS? How many people have put a 4 1/8 crank in an LS? The crank fits, but the stroke don't fit. Why? Because it pulls so much of the piston out of the bottom of the cylinder, it's doing somersaults every time it comes through bottom dead center. I just had a customer bring one to me. Things burning oil like crazy. I've built this gentleman a 22-pound, 3mm oil ring. This should dry up the Titanic. Should not be a problem. But his oil ring is 80 thousandths from coming out of the bottom of the cylinder. This doesn't work. So I'll just make that simple statement. Just because the crank fits doesn't mean the stroke fits. We have to look at those things. Compartment volume in the bottom end. As the cubic inch goes up, the pan's got to get bigger. We have to give it more airspace. Don't fill it full of oil. Let it fill up with air. So always be very aware of rock-over, top dead center, and especially at bottom dead center. How much piston rock does the engine have? Very easy to measure. Put a dial indicator on it, roll it over, zero it out, bring it back, see how much rock you've got. Less is best. Pull apart a factory engine. You know, we were talking yesterday about, I heard Darren again mention this morning about, you know, that trickle-down effect of technology from racing into the OE world, and that's an absolute fact. But one of the things that the OE also has is tremendously thick wallets. They can R&D and research and test and test and test. I'll tell anybody, go pull apart a modern engine. Take it apart, measure how much rock over it's got. If you see anything that goes into double digits, there's something wrong. These things are almost always in the low single-digit numbers. They've got the piston shape so dialed in on these things. Where I'll see aftermarket pistons done 60, 75, 80 thousandths rock, and they wonder why they have ring seal problems and blow-by problems. It's not a ring problem. It's not a bore problem. It's a rock-over problem. So you got to work with your piston guys. I'm trying to move it along real quick. I'll touch on this one, and then I'm going to turn it over to Ed. Gas porting. One of the newest things that we're working on is actually what we call gas-ported piston rings. Gas ports are essential if we're going to tighten up the clearances between the ring and the ringland. The gas pressure gets in between the clearance between the ring and the groove. We have to gas activate that ring. The ring will not do its job sealing correctly if it's just left on its own tension. Air compressor, yeah, we can probably get away with it, but we add heat, we add combustion, we see internal cylinder combustion spikes excess of 20,000 psi, very, very high pressures in there. So we tighten up that vertical clearance. We want to get rid of ring flutter. We want to increase ring-to-ring groove seal. So we introduce the gas port. And the gas port's a great thing as long as it's in the right place. So if you look at these illustrations, you'll notice, and it's kind of over-exaggerated, the gas port stops just before it intersects what's known as the root or the inside diameter of the groove. This allows the ring to block the gas port off on the intake stroke. It allows the gas pressure in, but eliminates that leakage path coming back out around the ring. So any of you guys that run and out in the world, I know lots of people, thousands and thousands of gas ported pistons get built out there. Look at that gas port on that engine on disassembly. Look for it to be gooey, gummy, wet, oily. You see all these black swirly trails coming back out of it. That's reversion on the intake stroke. That is all the gas coming back through the gas ports that are underneath the rings, oil included, contaminating that clean intake tract that you've got. It's contaminating the combustion chamber with nasty stuff that's going to kill the efficiency. That's a gas port that more than likely is not in the right location on the piston. So you want to kind of look at that. Just because you bought a gas ported piston doesn't mean it's in the right place. And I'm not beating on any of the piston companies out there, but we have to pay attention. This is all those little details that we really got to look at when we're assembling. So this is an example of that. You look at that piston, you see all the black stuff coming back up out of the gas ports. That's reversion. That is contaminating the intake tract. If you also look at the cylinder, notice the vertical lines in the cylinder next to it. This is out of a 410 sprint car engine. The gas port is a fixed location. We've got alcohol. That's actually showing you how the gas loading in the cylinder is not uniform. It is concentrated at the gas port. Creates a high pressure spot. Putting it in the piston ring itself, the ring is rotating. The gas port now becomes self-cleaning. Just think about like a keystone ring in a diesel. Why do we have a keystone ring? Because it's always cleaning itself. It's always cleaning all the carbon deposits off. Having a gas-ported ring in the engine eliminates that problem. It also allows you to use shelf pistons or kit pistons. Again, how many guys build an LS? It's not forced induction these days. None. Everybody buys the kit piston, going to put a turbo on it, 25 pounds of boost, and they don't have a gas port. You can simply add the gas port by putting it in the ring, and now we have a gas-ported piston, per se. It's actually in the ring, but they can buy the kit piston. But enough of my yammering. I appreciate everybody. I'm turning this over to my good friend, Ed.
Thank you, Keith. So, we're talking about piston rings and we're talking about blocks and we're talking about materials and we're talking about all these things. And we, as a company that builds honing machines, get this question all the time. I've been honing for 30 years. I've never had a lick of problem. And now I got all these oil burners. What in the world is going on, Well, things change, abrasive change. Hardness of the blocks change, materials in the blocks change, piston rings have changed, the coatings and all. In fact, this is a great example. This is, thanks to Mark Malberg, he took a moly piston ring and did a 3D print of it. And so I'll pass this around to the people that we have here in the audience, but this is a moly 3D printed, face of a moly ring 3D printed. So as Keith was talking earlier, you see the ability for that ring to hold oil. It's incredible. I mean, it's like a pond there, with the oil, okay? So you could finish a cylinder oil just about any way you wanted to finish it, and that's going to seal up, all right? This, on the other hand, is a steel ring with the DLC coating on it, all right? And if you compare the two, it's night and day difference. Obviously, there's nowhere or very little area there to hold oil, okay? So as we said earlier, oil is the sealer. So we've got to have oil somewhere. It's obviously not going to be on the face of that ring. That's why the you hear now, or the rage, or the technology is it's called plateau honing. That's the reason that we have to plateau hone. We have to be able to keep that oil somewhere. And so since we can't put it on the face of the ring, we now have to make the cylinder have the ability to hold more oil. And that's where we come into the plateau finishes. So we'll go step by step, but we get into like materials. So the same thing you have with materials. You see cast iron is 150 to 180 Bernal hardness, and we go through ductile iron is 2 to 250, and then we get into the hybrid ductile iron, which is 250 to 300. So I can tell you that honing a standard cast iron block versus a hybrid ductile iron block, you are not going to use the same abrasives, or you're not going to use the same technique, because the abrasive that will give you a RZ, we'll just pull out numbers out of the air here, but abrasive that'll give you, say, a 400 RZ in a cast iron cylinder is not going to give you a 400 RZ in a hybrid ductile iron cylinder. It's just not going to happen.
Something to notice as well is if you look at the pictures, not only are we talking about the hardness, but look at the grain structure of the materials. They're very, very different. That gray cast iron, the lower hardness, it's like how many people cook with an iron pan? What do you got to do to that iron pan to make it work? You got to season it.
Season it.
Same thing with that cylinder. That material is so porous, it actually holds oil on its own. So again, we can get away with certain things, but what happens when you take that material and you put 50 pounds of boost on it, make 2,000 horsepower. Well, you blow the bottom end about it because it's so porous, it cracks easily. We move into the harder materials, and the harder materials don't want to hold oil.
So during the whole process here, we have to create, so again, here are some 3D printed examples for the audience. This is a standard single finish, say 280 grit, standard abrasive, and this is a plateaued finish, all right? So I get this all the time. I get customers that say, well, I'm using this 280 and I just eased up on the pressure and I've plateaued the cylinder. You have not plateaued the cylinder, okay? It's just not possible. And so then I also get the customers, and I know you've heard this too, I'm going to use a 220 grit and I'm going to take it to within a thousandths. Then I'm going to use a 280 grit and I'm going to take it to within a half a thousandths. And then I'm going to put a 400 in there and I'm going to take it to 0. All right. Again, you have not put a plateau on there. What you have done is simply put a base finish of a 400 grit abrasive on there. We're talking millionths of an inch when we talk about plateau honing. It's literally, for any of you that have done it, you can't measure the amount of material you take off. It's simply, you know, a few millionths of an inch. And that brings up just a quick plug for Rottler. One of the hardest things to do is to try to plateau hone properly when you're trying to control the pressure and count strokes. Okay, so it's real important on the newer machines. They have the ability to go into what we call a plateau mode, where you determine the pressure, you determine the strokes, and you push a button and the machine does it for you. Takes the operator technique completely out of the equation. Super important. So again, you can kind of see in the slide there, there's no plateau versus a nice plateau. So what do we got there? Pressure contact. You want to? Yeah, take over for pressure versus contact area.
Am I live?
You are.
Guess I'm here.
Push the button so I can see what you're talking about.
So what we're talking about, the reason we've got a plateau is, you know, as you saw in the previous slide, we had all those peaks, all that valley. Well, if you look at what we were talking about unit pressures earlier, and again, it's kind of hard to see on the smaller screen, but if, you know, 100, you know, if I've got 500 pounds per square inch pushing against that cylinder wall with absolutely two flat surfaces, I've got 500 pounds per square inch of contact area. So I come in and I hone my cylinder, and, you know, Mark is obviously much more better versed, you know, well versed at this than I am, but you know, I have no plateau. So what do I've got? I've got lots of peaks. I've got very, very little contact area between the two. I've only got 10% plateau in that bore. So what do I have? I've taken my 500 pounds per square inch, I'm turning it to 5,000 pounds per square inch. So I'm going to have a lot of accelerated wear. I'm going to have a lot of material down in the bottom of my pan. We've all had those engines we've taken apart, and we've come out with all that fine material going, wow, what's that? That's your cylinder wall. That is the rings plateauing the bore, because they do this themselves over time. Why do we have to plateau? One, we don't want that wear metal going through the engine, and today, nobody wants to wait for that ring to come in. They want it in right now. This is the age of instant gratification. So as we start plateauing, we knock the tops down a little bit, or the rings wear it in. Now I've got 40% plateau in the cylinder, and I'm looking at about 1,250 pounds per square inch. As I go further, Mark talking about, looking at the, good Lord, I completely lost the number.
RMQ.
RMQ. I knew that was it. I start looking at numbers where I'm looking at my material ratios. I've got 80% plateau. So now I'm down to 625 pounds per square inch. Now I've got a reasonable number. I don't have as much wear. I don't have as much heat. I'm not creating as much friction because I've reduced the amount of contact area. I've increased the ability for that surface to hold oil and, again, keep that part lubricated. If you go back to 10%, that thing's not riding on the oil. It's riding on the cylinder wall. Now at 80%, I'm riding on that film of oil instead of riding directly against the surface itself.
So one of the, Mark has talked about surface finish and trace boss. And I think trace boss is one of the greatest things that this industry has come across in at least 20 years. You know, I always adhere to, you can't improve your process if you first can't measure it and know what's happening. And so, you know, through the years, we've had RA, and that was kind of the measurement to go by. Everybody went by RA. And this is just an illustration of what RA really tells you, 0. All right? Those two finishes are the same RA. Now, obviously, one's going to probably seal up pretty good. Oh, the other one might seal up pretty good, but it's not going to last very long. So we've gone from RAs to the RK parameters, and now we have trace boss. And I completely agree with Mark and Ryan's assessment. The visual is so much better than just numbers. It gives you the ability to really see what numbers mean, and it's just a tremendous asset in my opinion. And I kind of alluded to this earlier. You know, we're talking about microns, and this is just an example of a micron. You know, a human hair is 3/1000ths of a diameter. Okay, so you can see where the micron actually relates to a human hair, and that's what we're talking about when we're talking about plateau honing. It's not a rough and tumble operation. It's a very precise operation in order to get the proper RVK, RPK, and RK. And excuse me, Keith, you want to talk a little bit about that? Because I mean, we go by what you guys tell us.
So we work with a lot of companies and we do a lot of testing, and these are some numbers if anybody wants to capture this image or just contact me, I'll gladly send it to you. These are some basic numbers, and like Mark said, Ed said, you know, the numbers, I like to say, it'll get you into the zip code. It'll get you in the general vicinity. Okay, now we're in the right area, but now we have to start really looking at the image. And these are basic numbers for basic applications. Now we can, you know, if you start getting into something more specific, you can contact me. I'm working with some people right now that are working on what I'll refer to as an exotic fuel engine, and they're simply working with RA. And I am gently and carefully and slowly beating them into the head, trying to understand that these, you know, don't mean anything for what you're doing, but yet they're the numbers they've been working with for 30 years. They don't know any different. I'm trying to get them brought into the modern world. So in their application, which does not have a lot of combustion temperature in it, the numbers are going to be completely different. So if you've got a specialty application, just reach out. Contact us at the shop. Reach out to Ed. Ed knows. And we'll get you pointed the right direction. But it's just a zip code. And it's a great place to start. But most applications, most of your 90% of what's out there, the values you see here, RPKs, you know, 10 to 15, RK in the mid 40s to 50s, VK numbers 50 to 60. It's a great starting point. And I always like to use the word ish. In that area, ish. That's about where you want to be. And if you lean a direction, I'll always say this, and people can disagree with me, if you're going to lean a direction, lean to the high side. Rings, plateau bores, they are going to wear that finish down. So if we start a little high, they will, you know, we want to be in the right general area. We want to be able to, you know, get it and have it happen pretty quick. But if I lean a little high, as we like to refer to, the metal taker offer works better than the metal putter honor. It will bring the numbers down on their own, but it certainly can't go the other direction. So these are all great general starting places for numbers to begin with. And I'm going to turn this back over to Ed right now.
Yep. So as I said, Rottler, we are not experts at what cylinder wall finish you need for what particular piston ring. We're not that guy. That's the guy, okay? So we're just smart enough to be able to give you what they want. And so in order to do a plateau finish, you first have to start with a rough abrasive. That's the key in this whole process, is making sure that the initial roughness is rough enough to take off the peaks and leave you with the proper RVK numbers. And you can kind of see there's a good example of, you know, the first block is, or the first picture is just a roughed up cylinder, and the next one is with so many plateau strokes, and then the last one. And so that's the nice thing about this. I tell customers all the time, one of the other parameters that I use is RZ. Okay. Okay, I'm jumping ahead. Yeah, sorry. All right. So you know, I use the RZ parameter as kind of my bellwether as to where I need to be. You know, I get customers that go ahead and use let's just say a 170 grit, and they plateau it 5 strokes or 10 strokes or whatever you want to plateau it, and they start looking at RVK numbers and they're not high enough. Well, you can't get there. You know, you have to start with a rougher abrasive. So I always tell customers, you know, if you've got 3/1000ths to come out, hone 1/1000ths out of the bore, check your RZ. You know, compare it to what your other RZ was. That's a nice thing also about Trace Boss is you can save all those numbers, and you can save those graphs. And so you can kind of go back and forth and look at what you had done in the past, and was it successful or wasn't it? And yeah, this is a typical finish. I can't even read that. What is it? 6 on your RPK, 94 on your RK and 95 on a RVK.
So one of the things to take in here, and we talked about the numbers a lot, and like I said, the numbers are a great way to, they're a way to get you into the right zip code. You know, you're getting real close. But as Mark referred, referenced, we've got to look at the visual. I have a very good customer of mine, builds a lot of 410 sprint car engines. I work with a lot of these guys. And he kind of sent me a little trick thing in my, texted me. I was at a guy's shop, and I get these texts from him, and he sends me 2 different images using TraceBoss of 2 different engines. But yet the numbers were so close to each other, it was incredible. But when you started looking at the curve, or the ratio curves, one was a little flatter than the other. But yet the numbers were really, really close. The other thing you looked at when you're looking at this picture is what I want to call the consistency, the repeatability of the peak and the valley. So one engine had a trace that had very, very consistent valleys, very uniformly spaced peaks, really beautiful. The other cylinder, which again, when we looked at all the numbers, because we're averaging, were almost identical. But it had more widely spaced valleys and more sporadically deeper. All of a sudden you'd have, I'll call it that anomalous valley. And then we had this. And then we had another one of these. He goes, which one of these are you think is going to be the better of the 2? And I said, well, the second trace, which was the one that was very consistent. He goes, yep, it was 10 horsepower better and it pulled 4 more inches of vacuum. He goes, just in that. But yet, when we looked at RPK, RK, RVK, RMQ, we looked at those numbers. They were very, very similar, but just enough difference in that consistency of the peak and the valley. The engine sealed up that much better, and that was the only difference between the 2 engines. So that visual, that reference, being able to look at that makes a huge difference. As Mark says all the time, we can't just live by the numbers. They'll get you in the right neighborhood, but the rest of it you got to look at.
Yep, absolutely. And I will mention, well, we've talked about RZ and what RZ is. It's the highest peak and the lowest valley. So that just gives you an overall picture of what the true roughness of a cylinder is before you start knocking off peaks.
So I'll touch real quick if you don't mind.
No.
Where RZ comes in really handy for me is I get a lot of guys that call us and want to know what stone do I, well, first of all, again, those of you that have seen me do this before, they always ask me what grit.
Yes.
And I say, what the hell's that got to do? And then grits are something you cook on a stove in Alabama. What's that got to do with this? So they always want to know what grit to use. And I said, well, what's your application? And we talked to us. And when we first started messing and really looking at these numbers, one of the things that happened all the time was people would get their RK and their RVK flip-flopped. And what that tells me immediately is you did not have enough peak to valley height to allow us to properly plateau that bore. Tells me you did not use an aggressive enough stone to lay in that base. Or with the old way that we used to hone with these multiple steps, like Ed said, well, let's bring it within 2 of size with a 220, and then we're going to bring it to a half a size with a 280, then we're going to bring it to size with a 400, and then we're going to hit it with a plateau brush or a dirty diaper or whatever it is you decide to use to finish it with to do all that work. Well, we've killed everything. If anybody wants to look back, there was a white paper drawn up a long time ago by a gentleman named Hans Fischer. And Hans, I don't know if he worked for Sonnen or consulted for Sonnen.
No, he worked for Sonnen. He was actually my boss for a while.
There you go. Hans wrote a white paper up years ago about what he called extreme plateau honing. And his method was 60 grit to size, finish it with a 600 grit. But you want to know what? He showed the traces. He showed what he was doing. He was absolutely correct. The process was correct. Now, do I agree with 60 to size and 600 to finish? No, I don't necessarily agree with that. But again, it depends on the application. But the premise was correct. So coming in with a very rough stone to get that base, to get that RZ, to get that peak to valley, and then finishing with a fine stone to level it all out. And the number that tells me which stone we want to use to bring it to size is RZ, peak to valley. So if I've got a guy doing a crazy pulling tractor, 250 pounds of boost, pouring fuel through it like it's coming out of the Valdez, that guy better have an RZ that's in the high 400s, close to 500 to have enough peak to valley so that when he plateaus that down, he's got a lot of depth, a lot of oil retention. It tells me the right stone. But if he went to hone that and he calls me and says, yeah, I've got an RZ at 220, well, you better try again. You're never going to have enough there to be able to actually plateau that cylinder.
No, that's absolutely right. That's
RZ is a
the key.
very, very important
Yep.
figure.
And I even suggest that customers, they put that rough stone in, they hone it, they check their RZ, you know, and if it's in the ballpark, then continue to size and finish with your plateau. So
And if it's not, what do we do then?
then you go to a rougher abrasive, you know, in midstream. And then the other thing that'll tell you, we're talking about different parameters, RK, RVK, and RPK. You can tell immediately on a cylinder that has not been plateaued. They think they've plateaued it again, but you know, it's like a single grit finish. The RK and the RVK will be completely inverted. You know, your RK may be 80 and your RVK is 40. All right. I mean, it's immediate. There's just no guesswork into it. That's a single finish or single abrasive finish, you know, so real easy to tell. So then we get into abrasives, you know, and for years everybody run vitrified abrasives. All right. They work very well. You know, they do a good job. The problem with vitrified abrasives is as the materials have gotten harder, you have to change your bond strength all the time. So, you know, if you're using vitrified abrasives, you might have a soft stone for doing the higher Brunel blocks, and you might have a soft or a hard stone for doing the softer blocks. And so you end up with just racks of abrasives, you know, for the same size but different applications. And so, you know, the invent of the diamond abrasive and the CBN abrasive has really helped the situation. You know, diamond abrasives last forever. I tell the story, if you're using just a standard abrasive, you're probably, and taking 0.003 out of a V8 block, it's probably costing you about, I don't know, maybe they had a price increase, but roughly about $2.50 of abrasive cost per block. On a diamond abrasive, it's a nickel per block. I mean, it's dramatic. It doesn't seem like it when you're purchasing that diamond because that diamond's expensive, but those diamonds, I've done testing in production engine rebuilders, and you're going to average 80 to 90,000 bores per set of abrasives. So it's incredible. There's customers that had their same abrasives for 9, 10, 11 years, you know. They wear very well. What the detriment to a diamond is they're a very tough abrasive, but they're not a very sharp abrasive. So they plow and they tear and they fragment the metal, and so that doesn't end up with, you don't end up with a good clean finish for your rings. And I always use the analogy, you know, if you pull a little 1x1 stick through the dirt, you get dirt on either side of the groove and you get a pile of it at the end. Okay, if I pull a stick through the dirt that's sharp, I don't get that mounding or that abrasive or that wad of dirt at the end of the trough. So what we've done, and this is really through Keith's help, you know, we were we were diamond abrasive, and then we'd go in with a plateau honing tool, a brush more or less. And, you know, Keith was good enough. We were doing Darton liners and sending them to him, and he was taking pictures and looking at them under a microscope, and he said, man, I just don't like the finish. You know, he says it's still not crisp and clean. And so I said, well, I got an idea. Let's try some stuff. And so we experimented with CBN for quite some time. And CBN is a very sharp particle. It's not dull like diamond is. And so it cuts very cleanly. And so what we've determined is the best way to do this is go in with the diamond to create your valleys and your peaks, and then knock the peaks off with the CBN. It's an excellent process that works quite well. This one, right? Yep. And, this is, okay. So when we talk about, this is...
I just got to say, it took me about a half an hour to figure out how to get that stinking image in there out of TraceBoss, convert it into a PDF, to get it into the PowerPoint. So you got to use it, Ed.
I'm going to use it, yeah. So one of the things we get now is you know, there are a number of abrasive manufacturers out there and they all have diamond abrasives, and we list it as grit sizes, okay? It's 170 grit, it's 200 grit, it's 220 grit, it's whatever. And there's some, I'll call them economy abrasive salespeople out there. You know, their abrasives are considerably cheaper.
Pacific Rim?
Yeah, could be. And so I started doing some experiments, and I get customers that call me all the time, and they say, well, I'm using this. Well, is it our abrasive? No. And I'm not trying to push our abrasives, and I'm not trying to say that theirs are bad. What I'm trying to explain to customers is it's not just the grit size that creates the surface finish, okay? It's what we call the matrix. It's the mixture of diamonds and the bonding agents, okay, that create an abrasive. And from lots of practice and lots of running, we know pretty well what our abrasives will generate. And you throw somebody else's abrasive in there and they're getting different numbers, I'm like, I'd love to help you, but I don't know what their abrasives are creating. So I just wanted to throw that out there. This is, so what I did here, just to kind of prove the point, I can't read that. What's this one? Okay, so this is a 170 grit diamond that we normally run, okay? And you can see your RPK, RK, and RVK numbers. That is a 170 grit diamond, and you can see the difference. There's 30 points difference in RVK. That was simply created by a different matrix, a different mixture of the amount of diamonds versus the amount of bonding agent, okay? So, you know, something like this might work well in a sprint car, okay? But the other one wouldn't, you know? So I like to explain that to people because it's a big factor. I'm not saying anything about the other people's abrasives. They may work very well, but they have to do they got to put in the time, all right, to know what their abrasives are giving you in a particular cylinder.
Like I said, grits are something you cook on a stove in
That's
Alabama.
right.
Really good with butter on the top.
Yeah. You want me to do the Slinky? Okay. So this is one of Lake's favorite slides. And what we're trying to show there is it's back to, and Mark elaborated to this quite a bit, is bore geometry, okay? You can have the best finish and the best set of rings in the world. And if your bore geometry is bad, you're toast. You're not going to seal the thing up. And all this is to prove is if you were to inside mic that would be the same size all the way around. But the piston and the ring are not going to go up through that very easily. So,
Is it straight but is it round?
But is it round, right? And this is, again, Mark alluded to measuring equipment. And this is what we call an inkometer or a pat gauge, and they are extremely expensive, as he alluded to. But it's very telling. I mean, those particular pictures, you're only talking about literally microns of an inch. But it looks like, oh my God, I'd never run that cylinder. But they're actually very straight. So most people can't afford an inkometer. I'm not even sure they're still in business, but
Hummel still makes them.
Hummel makes them. Yeah. Yeah.
Oh, they stopped?
Oh, they quit making them too. Oh, okay. So one of the things we did at Rottler is when we began to develop the diamond hones and the abrasives, we took a 4-stone, a 6-stone, a 8-stone, a 10-stone, and a 12-stone, and we bought several of the Big M dart blocks, and we honed them, and we sent it off. That's when they were still in business, and you could send it up to Michigan and have them tested. And so we tested that. And the general statement is the more abrasives you have in a cylinder hone, or in the hone head, the rounder the cylinder is going to be. So 4 is much better than 2, 6 is much better than 4, 8 is better than 6, 10 is better than 8, and 12 is better than 10. There is a law of diminishing returns. We figured out that the 6-stone was the most economical and gave you the best bang for your buck. So the reason I say that is 8 stones, 10 stones, and 12 stones, you get a much smaller diameter range per hone head. They don't have the ability to go from, like our 6-stone hone head will go from 2/700 all the way up to 7 inches. The other hone heads with the 8, 10, or 12 stone, you get about maybe an inch range on them. So you've got to have 3 or 4 hone heads, and they are about 4 times the price of a standard hone head. So, and they have more moving parts in them, so a little bit more maintenance. But they are available, and they do work well. We just haven't found enough performance increase or betterment to say, yep, you ought to run a 12-stone. You know, the 6-stone works very, very, very well. And then, of course, you know, again, we're back to roundness. And obviously, a torque plate installed properly with the same bolts that you're going to put the head on with the same lubrication, makes a huge difference.
So one of the things I want to touch on with torque plates is just because you put a torque plate on it doesn't mean you necessarily made it better. Right. I've used a lot of torque plates that actually made it worse. They did not replicate what the cylinder head did. A long time ago, I did an LS, honed it, ran it. I was blown away at how bad it was, and I'm like, well, I used the torque plate. I did what they said. So I decided to put the torque plate on it, and I drew myself a little clock. 12 o'clock, 1 o'clock, 2 o'clock, all the way around. Took my dial bore gauge, because it's the only tool I had, don't have an incometer, and I mapped it. Okay, here's my sizing all the way around with my torque plate on. I then decided to take the torque plate back off, put the cylinder head back on, flipped the block over, came in from the bottom. Guess what? They didn't even do remotely the same thing. So I then figured out what I needed to do with sequence and yield on the torque plate to make the torque plate do what the cylinder head was doing. Voila, problem solved. There's a lot of guys out there. I'll put in a plug for our friend Brad Lagman at QMP right now. Brad's torque plates look like a cylinder head. Height, stand, water jackets. He does everything he can to replicate what the cylinder head does when it's bolted onto the block. So don't just trust the plate. Check it. You've got that dial bore gauge, put the head on, flip it over, make your pattern, see if the plate's doing what the head's doing. Don't just assume that it's doing the right job. Not picking on the torque plate, guys. They make a tool. It's how you use that tool. So, but we're talking about that trickle-down effect of racing into the OE world. What's happening now? The next evolution into the OE world. So if you can imagine, you're not going to have a guy standing at General Motors, standing in front of that automated hone all day, putting torque plates on and off a block. It's just not happening. It's not going to work in the production world. So the next evolution in what they're doing is what's called pattern honing. Through the use of computers, they're actually figuring out what is the shape of the bore while the engine's running at temperature, and how do we create an improper shape at ambient temperature so that we get the correct shape while it's running. They have actually developed that technology, so they're purposely honing the bores out of shape so that when the cylinder head's on and it's at running temperature, the bore is actually straight and round. So we'll say that's what's coming down the pipeline. So they learn from us, but then we learn from them. They're able to, we'll say, spend the money to develop that type of technology, and that's what's coming down the line. When are you going to have that feature, Ed?
Yeah. I don't think I'll be around. So we talk about, excuse me, proper crosshatch angle. And again, we're not, at Rottler, we're not smart enough to tell you what crosshatch angle you ought to have. We leave that up to the ring guys, okay? Typically, I think you talk about 38 to 45.
So when we talk about crosshatch angle, first thing to be aware of, or just we'll say cognitive of, is we're talking about what's called the included angle. So we're talking about the angle between the up and the down stroke. So most of us don't have USB microscopes. We don't have the ability to look at that. Now, if you have trace boss, yes, you do, and it's real time and it's really cool. I've used it for all kinds of stuff. It's really very accurate. But if we're using just rudimentary techniques, we're going to use a plastic protractor. You can take a plastic protractor, put it in the bore, zero your horizon lines, the deck of the block. You can measure the angle coming down off of that, and it's going to be double that. If you've got 22 degrees coming off the deck, it's 44 degrees included. But One of the things to also look at with that crosshatch pattern is the consistency of that crosshatch. A lot of guys with the older manual machines, well, she's a little tight at the top, a little tight at the bottom. They'll sit there and dwell up there and spin that hone round and round and round and round and round and create that nice horizontal pattern going across. And then they'll come back in and swish it 2 or 3 strokes. And if you look at it, it looks fuzzy. It looks distorted. They're laying a pattern over a pattern, and that just plays havoc with the rings. They don't like that. We want a nice consistent pattern top to bottom. And part of what the crosshatch does is help determine how we're moving oil either up and down the bore or side to side. The more vertical or steeper the crosshatch angle, the easier it is to move oil up and down the cylinder. The flatter it is, the less easy it is to move oil up and down the cylinder. It wants to move it left to right or side to side. So depending on the type of application, crosshatch angle can come into play. Very high RPM, very short stroke engines today, like in our racing world, we're running included angles at 25 degrees, 28 degrees, very, very flat crosshatch angles. Longer stroke engines, and one that's not a long stroke, but they use 60 degree all the time, is a Subaru. Flat engines, a boxer engine. They're not trying to get the oil to the top of the bore, they're trying to get it back into the sump. So they're using a steeper crosshatch angle to facilitate getting oil back into the pan. But look at a Harley. Harley-Davidson. Harley runs a 60-degree crosshatch angle. Why? Because if you look at bore to stroke, it's a relatively long cylinder. They're trying to get oil to the top of the cylinder. Same thing with aircraft engines. You'll rarely find an aircraft engine that doesn't run a 60-degree crosshatch angle. Why? Because they're trying to get oil to the top end. So crosshatch angles can play a lot to do with proper ring seal. So again, we can help guide you down that path, but don't be afraid to experiment. I had this conversation earlier today. You know, the only way to find out if it works is to try it and see if it did. If it failed, well, we learn from that failure. We come back, we try something different. We all want to cushion that blow as much as we can, but don't be afraid to experiment. Oh, come on. No. Break-in. A lot of people ask us about break-in. We're wrapping this up right now. Sorry, we've gone a bit long. But break-in process, one of the things that we don't want to do is just let it sit there idling. Again, people ask every day, well, how do I break it in? How do I run it in?
Tell your story.
Which one? I got a million.
The run-in stand.
Oh, the run-in stand. I've got to be real careful because, you know, I'll get a target on my back. But one of the things that run-in stands are great, and they're great if you use them in the right way. So we fire that engine up, we make sure it doesn't leak, we check the valves, we do everything to it, and then we shut it off. One of the things that drives me crazy is all the guys that call me up and they said, well, yeah, I ran it for an hour and a half, and, you know, man, I listened to it and it run great, sounded great, it's fantastic, blah, blah, blah. I'm like, well, you realize you got to put a load on it to make it work. This is what we have to do. We got to make it work. We got to make it work to burn all the fuel. What happens if we don't burn all the fuel? Fuel dilutes the oil. Oil is no longer oil. We start burnishing cylinders. Next thing you know, we've killed the block. Why? Because we didn't make it work. We want to make it work right away. I'll get guys with motorcycle stuff. You know, they fired it up. You know, they read online that you got to let it run for 15 minutes, and you got to shut it off. You got to let it heat soak for 25 minutes, and you got to fire it back up, run another 7.5 minutes, shut it back off, let it idle. You know, let it sit for 7 minutes, and start it back up. And I'm like, why? Well, you got to heat cycle all this stuff. No. When was the last time you went to the dealership, whether it be a car, truck, bus, or plane, and they said, oh, now go out in the parking lot. We got to heat cycle that thing for 2 hours. No, you got in it and you left. You're proud of your new purchase. And if you're someone like me, first thing you do is step on it. I don't want you to go out there and beat the thing to death. I don't want you to take it to 11,000 RPM right off the bat, but we need to get a load on it as quickly as possible. We don't want to let it sit there running unloaded. Get it up to temperature, get a load on it as quickly as possible. If we can get it on the dyno, that's excellent. If it's going in the vehicle, try to take it somewhere around here. Run it up and down the hills. Go have some fun with it. Don't beat it to death, but don't baby it either. And then I'll also say, where did it say in the book that you got to break your camshaft in sitting in your driveway? Keep the RPM up, go up and drive it. We've got air coming across the exhaust system, cooling everything. I'd never break a cam in sitting in my driveway. Then again, I haven't run a flat tappet cam in 10 years.
No, I haven't either.
I've never adhered to it's got to sit in my driveway while I do it. Get it out, run it. But get a load on it as quickly as you can. It's the best thing for the rings. And with that, thanks everybody here, out there. Appreciate anything. If you have any questions, we're here to answer them. Thank you.
Thanks.
I got to make a statement.
All right, he's going to nail me to the wall now.
Uh-oh, he's got the finger out.
That was the most clear, concise presentation of 40 years of piston ring, cylinder wall, I've ever seen. First,
Thank you.
nobody here, I don't think, really had to live through the living hell that it was to try to seal up a high-speed engine in the 90s. well, many races were won or lost by if you could even maintain rings for the race. And we had to go out and educate the ring companies and the machine companies what we need, and now you guys are educating us. This is awesome.
Well, thank you, Darren. I
Thank you.
appreciate that. One of the first conversations I had when I went to work for Total Seal, like I've said, alluded to, I've been Total Seal 28 years. Prior to that, in the performance industry, but I made a phone call to Warren, and I said, "What would you like?" Because I knew a little bit about rings. I knew I could go down and order my Speed Pro kit from Loper's Performance back in the day, and go out and have fun with my Chevelle. But I called Warren, and it's like, Warren, what do you want? What would you like in piston rings? He goes, "I'd like 8 rings that are the same." That was a light bulb moment.
Yep. Yeah. 20 years ago, I was calling on the cup shops, and I mean, they would literally have a sleeve of pistons rings, and all that guy did was stick one in a bore and light check it. One after another. I mean, that had to be a brutal job.
The quick seat's actually not a comet. It's actually just lubricant. So when we started with the quick seat, and we still service it today, it's very popular. It's just a lubricant. It's just a different way of lubricating versus oil. It stays in the crosshatch. It lasts longer, doesn't displace very quickly. So it stays there and just kind of protects the parts a little longer than most of the assembly lubes. But yeah, we still do quick seat. It's a popular product. Yep. Oh, absolutely. It does, but a very small amount. One of the things that I will say people do is they overuse it. That little 2-gram container, I can generally do 3 or 4 engines out of. It doesn't take a lot. Little bit. I put it on my fingers. Some people put it on a rag, and you just lightly tint that cylinder with that. It gets a little down in the crosshatch, and it stays there and slowly dissipates into the oil. So if you rotate the engine over and you get this black dust on the top of your bore, you use too much.
I'm sure nobody here does that, but for our audience out there, talk a little bit about, I know this is Lake's, forte, but talk a little bit about break-in oil and the differences. We use break-in oil to put into an engine, and I personally have a good friend of mine who's got the run-in stand, and he starts it up once in a while. I told him, Gene, you better quit that. But the other thing, he called me in an absolute panic the other day. He had left the break-in oil in there, and that motor sat for a year. And he was reading an article about that, and it said, there are no rust preventatives in a break-in oil.
Well, one of the things to keep in mind is, real race oils have very little in there as far as rust preventatives, things of that nature. So a lot of guys, I'll get customers that'll build a really, really, we'll say bad mama of a street engine, and they immediately go to a race oil. Well, they'll get problems where eventually it starts kind of coking up the bores and they'll get rust. Well, it's because it doesn't have those additive. It doesn't have a cleaning additive package. It doesn't have a rust preventative package in it. Why? Because it's a race oil. It's going into an engine. You're going to race it. You're going to change it. You're constantly changing these oils. So cars that, even though your street car may make 2,000 horsepower, it's still a street car. Some people get offended by that. I ask, what are you using this for? Well, it's 804 cubic inches and 7,000 to 1 compression. They go down this whole list of everything it is. But I go, but do you drive it on the street? Well, yeah. I go, well, then it's a street car. And I apologize. I'm not trying to offend you with that. I'm asking you how you're driving it, because street cars have to do things race cars never have to do. And one of those has to do with the oil. How often do we change that oil? Additive packages, rust preventatives, all this has a lot to do with the type of oil you use in that car. So we have to look at that, how it's being used. Now, there is no regulation on the word break-in oil. You can put the word break-in oil on any bottle of juice you want to put in it. Lake's taught me well. Mm-hmm. So you have to be very careful. Do your due diligence. Do your research about the brand of break-in oil that you're using. Again, I sound like I'm a commercial for Lake, but go to Speed Diagnostics. Lake's got all the information out there. He's tested dozens of different break-in oils, and he's given you the complete chemical breakdown of what's in that jug of juice that they call a break-in oil, and which ones are good and which ones are bad, and why. You want to look at a number called the TBN, the total base number. The lower that number is, the more of the reality it is of being a proper break-in oil. Because oil additive packages kind of lean two directions. Again, I'm just quoting Lake here, but you've got anti-friction and you have anti-scuff. Well, about everything in an engine loves anti-friction, especially camshaft products. What does a ring hate? Anti-friction. It wants friction. It needs to take all that fine material and wear those surfaces together, just like a lifter. it could be, you know, if one of our guys, Scott Deal, was here, Scott worked in the cup world for years, he can go back to the days with the flat tappet cam and when they started talking about ultra polishing the camshaft. I know Darren works with Billy all the time, and when they got these super smooth finishes on cams and lifters and then put super smooth oil in it, what did it do? It wiped itself out. It failed. It needed some friction to get those surfaces to work correctly together. So rings want friction. Camshafts don't want a lot of friction. We've got to find that right balance between anti-friction and anti-scuff. And again, plug in Lake, talk to Lake. He can explain all those differences to you. But finding the right break-in oil is very important. How long we leave it in, how we run that engine. And he's got a full breakdown on the website of what's in the break-in oils.
All right. Thank you. Thank you very much.
Thanks, everybody.